Hello viewers, welcome to AKGEC Digital School. Today we are going to learn an important topic of computer organization and architecture, that is IEEE representation of floating point numbers. Basically in this topic we will learn how we can store floating point numbers inside computer system, because in basically there is a problem with floating point numbers that we have a point with us with floating point numbers and we cannot store point inside computer, inside flip flop. So basically we have a binary number, suppose like 11.22, 11.00. So if you want to store that number, so we are not able to store that point inside computer system. So how we can represent, how we can store that particular number, we will learn in this topic. So first of all, we'll discuss some basic about what is IEEE. So IEEE is basically a standard for floating point numbers, which is a technical standard and established in 1985 by the Institute of Electrical and Electronics Engineering. IEEE standard 754 floating point numbers is the most common representation nowadays for storing floating point numbers in computers, in many computers like Windows, Mac or any other computer system. So there are three basic components while storing any floating point number inside computer system. One is called as sign, second is called as biased component, and third is called as normalized mantissa. So these three things are there. Sign is basically will represent with the help of 0 or 1. If the number is positive, we'll use 0, and if the number is negative, we'll use 1. Biased component, or we can say this also as true component, is basically needs to represent both positive and negative exponent. A bias is added to the actual exponent in order to get the stored exponent. This will basically give us the positive value only. With the help of this, we will get the positive number always. And last is normalized mantissa. What is normalized mantissa? In normalized mantissa, there is only one to the left of the decimal of the places. So we will learn these things in detail. Now we have two basic format in IEEE 754. The first one is 75432 for 32 bits, which is also called as single precision format or short real format. And second format we have with us is IEEE 754 64 bit, that is, which is also called as double precision or long real format. So these are the two formats in which we will learn to store our floating point numbers. Like our first format is of 32 bits, our second format is of 64 bit. According to the first format, we will assign 1 bit for sign, we will assign 8 bits for exponent, and we will assign 23 bits for mantissa, normalized mantissa basically. In double precision, we will assign 1 bit for sign again, we will assign 11 instead of 8 bits, we will assign 11 bits to exponent, and we will assign 52 bits for mantissa. Now we will learn step by step how to solve a problem. Suppose we have a number with us, so how to solve that number and how to represent that number in the format of 32 and 64 bit. So basically there is one more thing why we are doing it. Again I am telling you, because we cannot store point inside the computer, we cannot store dot inside the computer system. So because we cannot store dot, so there is we have a choice that we can use this format. With the help of this, we can store our any floating point number inside computer system without using dot. So first step for solving this, for representing this, is convert given number into a binary number. For example, just let's consider a number, say we have a number called 14.25. This is a number, suppose. This could be in decimal or hexadecimal also. So considering right now this number is in decimal. So first step of this is that we have to convert a given number into binary form. So 14 binary of 14 is 1110. Point. Floating binary of 0.25 is 0, 1, 0, 0, 0. We can use 4 to 5 digits after decimal. So this is my binary number. I hope you guys know about how to find binary of a given decimal number. So this is our binary number for 14.25. Now in this you can see that floating position is somewhere around after we have 5 places. So position of point is not fixed, position of point is moving. Suppose let's say another example, for example we have a number say A2 point, this is suppose an hexadecimal number, and if we want to convert this number into binary, so we will have 1010 for A, 0010 for 2, point 0001 for 1, and 1011 for B. So this is our binary number for A2.1B. So as we can see, the position of point is floating for different binary numbers. So our second step is that we have to normalize these numbers. So now we have to normalize our binary number. For normalization, there is only one thing we need to do, that normalization is the process of shifting the point, because our point is floating in given number. So normalization is the process of shifting the point either left or right, so that there is only one non-zero, and if we are considering binary number, so that non-zero number would be 1 only. So one non-zero digit to the left of the point. And this is how it will look like when we will solve, when we will represent our number into the normalized form. This will represent the sign, this will represent the mantissa part, and this will represent the exponent part, right? So let's take an example. Let's consider this number 1110.01000, right? So if we want to normalize this number, into the given format, so how can we do this? We need to shift this point, left or right, so that there is only one non-zero digit to the left of the point. For that, obviously we need to shift this point place towards the left. So if we'll shift this point towards the left, 1, 2, 3, that means we have to shift this point how many times? 3 times towards left. And for that we need to multiply with 2 raised to the power 3, because we have shifted this point 3 times towards left, so we are associated a number that is 2 raised to the power 3. If we have shifted 4 times, so we will write 2 raised to the power 4. If we will shift 10 times, so we have to write 2 raised to the power 10. If we will shift this point place towards right, suppose, yeah, so let's take another example in which we need to shift the decimal points towards the right. So let's take an example, say we have a number 0, 0, 0, 0, 0.0010. Suppose this is a number and we have the point position over here. So again we need to shift the number like this, that we have one or non-zero numbers to the left of the point. So in this particular example, we have to shift this number with this point towards right side. How much times? 3 times. So if we'll shift this number like this, so we will have a number called 1.0, because we can remove all these 0 towards left. If you want to write, you can, it's not a problem. And we need to multiply with 2 raised to the power minus 3 in this case, because we are shifting our point right side. If we are shifting our point left side, that then power will become exponent will become positive, and if we are shifting this point towards right, so power will become negative. And also we can see that this number is so positive, so there is we can associate minus 1 raised to the power 0, because any number power 0 becomes 1. So minus 1 raised to the power 0 multiply with this, multiply with this. So now it looks like this format. If you guys see, we have minus 1 raised to the power s, that is minus 1 raised to the power 0, 1 point m, 1 point this mantissa, and 2 raised to the power e. So this is my e. So now we can calculate three things: s, which is 0, m, this is our m, and this is our e, true exponent, right? So we have calculated the normalized form of the given binary number. So our next step is that we need to calculate the biased component, biased exponent. How we can calculate biased exponent? Biased exponent can be calculated with the help of true exponent. So as we have true exponent with this example is 3. So biased component for 32-bit is say biased component if we are representing with e dash, which is true component plus 127 in case of 32-bit representation. In case of 64-bit representation, biased component becomes true exponent, actual exponent plus 1023. So in previous example, we have the value of exponent is 3, that is a true exponent, actual exponent. So if we'll put this value over here, so what will be our e dash? 3 plus 127, that is 130. So e dash is 130 for 32-bit, and if we'll put 3 here for 64, so we will have 1026 e dash for 64-bit, correct? So with this step number 3, we will have e dash with us for 32-bit and 64-bit. Now our next step, we have to convert this biased component into the given binary form, means which we have calculated just 130 and 1026. We need to find the binary of these number. So if we are talking about the 32, we have value 130 with us, and for 64 we have a value called 1026 with us. So what we need to do is we need to convert this number into the given binary form. So this is again we have a decimal to binary conversion. I hope you have read this before. So 130, if we convert 130 into the binary, so we will have a number. So this is a binary conversion of 130, a binary conversion for 1026 with us. Now we have binary conversion for both, for 130 and for 1026. Then this is a last step. We need to substitute these things which we have calculated in a format which I have shown to you. In this format we have to represent now finally. Now we have sign bit with us, that is 0 because our number was positive. We have to put biased component over here which we have calculated, and we have to put basically the binary form of those. And last we have to provide the mantissa part, and this is our mantissa part. So now we need to put all these values which we have calculated in the desired format. So for 32-bit, a desired format is, for sign bit we need to use only 1 bit. So for that is 0. This is our sign bit. For biased exponent, I am writing e dash. We have to provide biased exponent in 8-bit. So we have calculated our biased exponent, and we can see that like this is 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So this has already in 8 bits. So there is no need to write any extra bit with this, so we are just putting this over here. So this is our biased component, and mantissa part will take 23 bits, next 23 bits, because this complete will take how many bits? This complete will take total 32 bits. So our mantissa is basically this after point, because there is no need to store point, there is no need to store this one, else it will take an extra step, or point we cannot store, as I have said you earlier. So 1 1 0 0 1 0 0 1 1 0 0 1 0 0. But as we can see that we need to represent this in 23 bits, but this is this number is taking 8 bits only. So you just need to incorporate 23 bits like this. We need to write 0 0 dot 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 0. So there is no need to write all 23 bits for mantissa parts. So this is IEEE representation for IEEE 75432 format. So in 32 format bit, we have a sign bit, we have our biased exponent, and we have our mantissa part. Similarly, we can write or we can represent a format for 64 bit. So again, for 64 bit sign will again, we have for sign bit we have again 1 bit, number is positive, so we need to place 0. For true for biased exponent we have 11 bits, as we can see over here. For biased exponent we have 11 bits. Biased exponent value is 1026, and for 1026 we have our binary number with us. And last one is our mantissa part. So for 64 bit, if this whole will occupy 64 bit, naturally tell me how many bit we have to provide to mantissa? 1 plus 11 12, rest are 52. So we need to represent our mantissa in 52 bit. But again, as I told you, our mantissa was like 1 1 0 0 1 0 0. So there is no need to write 52 bits. So we have to provide 0 0, and you need to just write dot, and you need to write this only. So this is a floating point representation, floating point number representation for 32 bit and 64 bit. And as you can see guys, there is no dot we are storing. This is the main agenda, this is the main reason why we are studying this representation, because in this given format there is no need to store any decimal point, and we are able to store this decimal number without using decimal point in our representation. So for sign bit we have a number. If a number, suppose if number was negative, so there is only one change, that this will become 1 only. Biased exponent we are writing because we don't want our exponent be negative, so we use biased exponent method to make them positive for 32 bit this and for 64 bit this. So I hope this is clear to you all. Let's take another example for negative number. Suppose we have a number called So suppose this is a number, negative floating point number, and you will you'll just see ki there is no need to there is no need to worry about this negative, because there is only one change we'll have for sign bit only, right? So first, so now we have these 5 steps. I'll complete all these 5 steps one by one for the number. Like we have to convert number in binary form, then we'll need to find the normalized binary number, then we have to calculate the biased exponent, then we'll have to calculate the binary number for our biased component, and then finally we need to represent a number into the desired format, right? So now this is my number. Let's solve this. Yeah, tell me what is the binary for a1 dot 2a. Yeah, tell me fast. Is 1010. We have to break each and every digit into the group of 4. So for a we have 1010, for 1 we have 0001, then we have a point over here, then we need to write that for 2, that is 0010, And for A, we have 1 0 1 0 again. So this is my binary. This is my first step. I have converted my number into the binary number. But again, position of point is not fixed in this number. So we have to what? Correct. We have to normalize a given number. So for normalization, we need to shift the position of point dot in such a way that there would be only one non-zero number to the left of the point. So for this, we have to shift this point towards the left. And how much places? 1, 2, 3, 4, 5, 6, 7. So we need to move this point 7 places towards left of this number. Right. So this is, I have fixed my floating number. Now I need to represent this number into the format. I hope you remember, minus 1 raised to the power s multiply 1 dot m multiply 2 raised to the power e. So as we have shifted this points towards left 7 places, so what we can incorporate here, 2 raised to the power 7. And for this negative number, we can write minus 1 raised to the power 1 this time, because minus 1 raised to the power 1 is minus 1, which will make this number as negative. Then we have 1 dot mantissa part. This is our mantissa part, right? We need to put this number here, and then we need to multiply this with 2 raised to the power e, that is 7. So this is a format from which we can easily understand that s is 1, e is 7, correct, and m is 0 1 4 times 0 1 0 0 1 0 1 0 1 0. This is a long mantissa we have. So this is my step number 2. I have normalized my number. Step number 3, we need to calculate the biased component. We have a true component, that is 7. So in step number 3, for 32-bit, calculate biased component. So E dash is equals to E plus 127. A previous E is 7. So E dash becomes 7 plus 127. That is correct. That is 134 for 32 bits. And for 64 bits, E dash becomes exponent plus 1023. So as our exponent is 7 again, so our biased exponent become 1030. So this is my step number 3. I have calculated my biased exponent. Now what I need to calculate? Correct. I need to convert these biased component into the given binary. So for 134 and for 1023. So step number 4, I need to convert my biased component into the binary form. So for 134, we have this binary number 1 4 times 0 110, and for 1030 for 64 bit, a binary number would be, so for 1030 a binary number is this. So there is no need to write extra bit, because this is already we have in 8 bits and this is we already have in 11 bits. So now this we have completed with 4. We need to represent these numbers into the desired format. So for 32 bits, my desired format again takes 1 bit for sign, correct. How many bits for biased exponent? 8. and for Mantissa we will have 23 bits. Now my sign bit was 1, so I need to put 1. My biased exponent is written over here, 1 4 times 0 1 1 0. And Mantissa part we have with us is this 0 1 4 times 0 1 0 0. One zero one zero 1 0. Again, this is shorter than 23 bits, so we need to again write associated few zeros towards right. So this is my representation for 32 bits. And last for 64 bits. Yeah, tell me how many bits for sign? Again 1, very good. For biased exponent, perfect, 11. And for Mantissa, 52, very good. So now we need to represent in this given format. Sign bit is again 1. Biased exponent we have just calculated over here for 64 bit, that is 1 0 0 0 1 1 0. So this number is already in 11 bits. And for Mantissa again we need to write for 52. Again we will not write 64, we'll just put some dots like this. Correct? So this is a final representation for the given number, that is minus a1 dot 2a. Thank you so much. Keep learning. Thank you.